So hi, everybody. For those who don't know me, my name is Eric. I'm one of the organizers of the AppliedAI Meetup, and I'm going to be your host this evening. The other organizers are Jen, Daniel, and Justin. If you're new to this meetup, I would like to extend a very warm welcome to you. If you've joined us in the past, thank you and welcome as well. One thing I want to highlight for you is that our meetup is always on the first Thursday of every month. We'll have one exception in July, and we will communicate that as we get closer to July. Our next meetup is on May 6th. That's the first Thursday in May. And the topic will be on AI and the IP landscape. So we have a very exciting speaker coming up who's been doing intellectual property for AI innovators for a very long time. So it's gonna be an awesome topic and presenter. So we hope you'll be able to join us on May 6th. One thing that we want to request is that please feel free to share with at least two people you think will find that topic valuable. One of the goals of the AppliedAI Meetup is to connect like-minded people. So same interests, let's make the connections. We have a Slack channel, and we emphasizing and promoting people to use it to make connections. So we'll share a link for our Slack channel in the chat. We also have an AI podcast called Conversations on AppliedAI. The most recent episode is, Justin talking to Bonjun, who's attending tonight, and he presented in our meetup in February. So please, when you get a chance, please give it a listen and share. Also, if you know someone who make a good guest, please reach out to Justin and we'll make it happen. So we're going to share a link for the podcast in the chat here. So watch out for that. All right. Thank you, Justin. At every meetup, we highlight a local meetup that's tackling topics complementary to what AppliedAI covers. And for this month, we'd like to highlight practical NLP. This is a study group focused on practical applications for natural language processing. And what this meetup does is they work on projects from a textbook called Practical Natural Language Processing, a comprehensive guide to building natural world NLP systems. It's a mouthful for that textbook, but I'll share a link in the chat as the presentation goes on. Okay, so now on to this evening's presenter. Our presenter this evening is Kevin Gu. Kevin is a colleague of mine. We work for the same company. Different divisions, different parts of the company, but nonetheless colleagues because we work for the same company. Kevin has a PhD in electrical and computer engineering. His research focus was computer vision and deep learning. Kevin is very passionate about the topic that he's gonna cover tonight. And how do you use conversational agents to deliver information? And that information can either be semantic or emotional. So how do you deliver this rich information to help patients? And it's for a particular group of patients. So those with low literacy, how do you use this information to help patients with low literacy to get a better understanding of their test results and the medical instructions they're getting from their caregivers and physicians? So one thing I want to say is Kevin is a very accomplished data scientist and researcher, and we're in very good company tonight. Very technical, so please feel free to ask questions as he presents. Also feel free to comment if you have like a good example that's going to be reinforcing and adding richness to what Kevin is presenting. Please feel free to chime in. So without much further ado, I'd like to present Kevin. Kevin, thank you for presenting tonight, please.
Thank you, Eric, for the introduction. Let me just share my screen, like so. Okay, and Yeah, so my name is Kevin Gu, and I graduated from the University of Illinois, Champaign, on the EC. So during my PhD, I'm more focusing on the computer vision and later on the thesis of facial animation synthesis. So I'm working with Professor Thomas Huang and Professor Mark Kawakowski. So the topic is a journey to photorealistic facial animation synthesis. And here is the outline. So I'll talk about a little bit about the background and motivation. And for my thesis, it's actually, I was divided into two parts. So the first part is, we call it the Avatar project. So this one is actually a collaboration between the EC department and the psychology department in the Beckman Institute. So basically, I'm more working on the engineering side of this part, and the psychologists, they do experiment and analysis. For this part, I will just go through very quickly because that's not really the major part of my work. Although it's a very, actually very important, I think it's a very useful research topic to explore. So the Avatar project. And for the main part of my thesis is mainly on the facial animation synthesis, either as landmark-driven or audio-driven. So we'll talk about it later. And also there are some other projects I've done along the way during either my master or early PhD education path. And yeah, and finally, there's a thank you slide. So let's just move on. So the first part is the background and motivation. So human facial animation. So I look it up online and says that there are basically 43 muscles under our face, and they have to be moved in a coordinated way to generate different kind of emotions. So Mr. Bean right there probably activate all of them at once. So traditionally, the emotions are categorized into seven categories. So like happy, sad, surprise, those kind of things. However, as we know that the human expression can vary in different intensity as well as across different categories. So it's more like more of a continuous space instead of just a categorical categorization. And in terms of generation, actually, it can generate both from voluntarily or involuntarily. So either controlled by our emotion or by the speech word and those kind of driving sources. And it's a very important nonverbal behavior. So basically, when they talk to each other, we feel much more comfortable and easy to understand each other if we look at them into the face, so that we can get both the verbal message as well as the nonverbal messages. So yeah. So at the very beginning, the facial generation is actually already started in 1972. So this one is a very simple model. If we look from today, it's just 400 vertices and 250 polygons. It's keyframe based, and so basically you generate keyframe by keyframe and then concatenate them together. And at that time, it's considered to be a realistic facial animation. And along the way, the technique has evolved quite a lot. So as if you see those movies like Tony Story or The Matrix Reloaded, you see that those computer-generated facial animation become more and more real. And also the Lord of the Rings, the Gollum, as well as the King Kong or Avatar, so they become very realistic along the way. Turns out there are many different techniques, and here are some of the most utilized in the industry. So motion capture or mocap. So basically, they place those reflected dots on the face, and they use the camera to track their movement of the reflected dots. After that, they just transfer this movement to another model, for example, this monkey, and to make the actual facial animation in the movie. So yeah, those basically films utilize this kind of technique, sometimes called performance capture also. And there's another one called blend shape. So basically, people predefine a set of facial meshes, and then they just blend them together by weighted them by different ways and subtract them together to generate the target emotion. The Lord of Rings, as far as I know, the Golem, a small monster, is actually generated using this technique. Oops. Yeah, like this. And also, I think there's a bone-driven system. So basically, this one is more like a physical base. So there are bones underneath the mesh, and the points on the mesh are assigned to each bone with different weights. And when the bone moves, the mesh also moves, simulating our facial expression. So that's another one. I know that it's used in some of the video games, as well as a VHT, Virtual Human Toolkit, which is the toolkit we used in the first Avatar project. And yeah, so there's a bone-driven system. There are also a texture-based system. It's not very popular. I don't find too much reference to it. I think one of the small movie called Black or White, I think this one uses a texture morphing-based system, but there's just not too much information there. And yeah, of course, there are different limitations and advantages, but basically the mocap, the performance capture is very realistic. However, it costs a lot. The equipment, the actors have to actually be there, so it's more expensive. Whereas other systems are usually much more less expensive, like the blend shape and the bone-driven system. They'll be much less expensive and generate a reasonably high fidelity facial movement. However, they need handcrafted templates, or they need a complicated modeling process, which requires some expert and human time. Yeah, so there are actually lots of applications for those techniques. So of course, in the gaming industry, and everybody playing video games, I guess. So the gaming industry, the facial animation generation is very popular. In the film production, of course, I mean, that's a main driving force underneath the development. And also in the teleconference and the video compression, so if we somehow, instead of transmitting the whole image, we can only transfer the movement of the face and then resynthesis it on the other side. So that is another application. Also the video compression. So basically we extract those movements from the video sequence and store them instead of storing every frame. That's another potential application. Also, there are some online customer service that utilize a chatbot or a chatbot with a animated face, to better mimic a face-to-face communication. And yeah, also the electronic health record system, which is the Avatar project I'm going to talk about, also could benefit from facial emission synthesis. Yeah, so that's a background. And here is the Avatar project. So yeah, so this one is a collaboration between the psychology department and the EC department. So here's the very basic motivation. So it turns out that the electronic health record system, or we call EHR, they are very underutilized. And the reason is that most adults don't have the sufficient numerical or medical literacy to understand those health informations. And however, most of the consumer actually wish to use the portal system remotely to access their medical test results instead of going into hospitals, and it's just more convenient. However, there is an obstacle, as you see, that the numbers are hard to interpret, and sometimes they don't understand whether the result is good or not. So the current EHR system, they are mostly in plain text format. So just a plain text with written numbers on it. And they have medical terms on it without too much explanation. That actually generates some problem, especially for the elder patients. And in this project, actually, we're trying to explore some potential solutions to that. So we want to use a conversational agent, which is basically a talking head, to enhance the message. And what do I mean by that? So basically, instead of only delivering the semantic message using plain text, we also want to deliver the emotional message by using the synthesized talking head. and in the hope that the patients can get a better gist level understanding of the underlying medical messages. So in the very original method, probably in 2014 back then, there's a in-house developed system basically synthesize a facial expression using a keyframe-based method. And so basically it's a combination between expression template and the keyframe interpolation. So basically they took a human face as a picture, and they just move those points around in order to generate different emotions. And those movements, they are predefined facial expression templates. So this one is actually pretty similar to the blend shape method we talked about previously. The problem of the original system is that it's not very realistic, especially when we try to combine the facial expression generated from emotion as well as from speech. So basically, let's say if we are smiling when speaking a word, our lip corner naturally raise up. However, we cannot really combine those linearly. It generates some very unrealistic result. So we try something by defining a expression template and a WASM template. WASM basically just means some phoneme we speak. So defining one template for each combination of those, and that turns out to work much better. So basically, the expression become more realistic with less artifacts. So that's at the very beginning. And we also have the audio synthesis into it, although it's done by one of my other colleagues. So that one I'm not quite familiar, but basically I think they use the unique selection method to concatenate different audio segments together to generate emotive speech. After that, we just synchronize the audio and visual by keyframe aligning. And after that, do an interpolation to generate a visual expression video with more frame per second, basically. So the psychology department also enhanced this kind of message by using some graphics. So basically, they put graphics on the left side to indicate the severeness of each test result, basically, and they color coded them. And they use this format to and present it to some human test subjects. And the result is published in the AMI this paper. I won't really talk too much about it because it's more on the psychology side, which I don't really understand. But basically, this is a combination between the computer-generated visual animation and psychology research. Yeah, just a little bit more detail. So we basically use cholesterol test, which is very popular among elder patients. And we assess their understanding by asking questions after watching the generated generated visual animation videos. So here are some main summation of the result, which I will not talk in detail here. But basically, the idea is as follows. Compared to the plain text message format, the enhanced computer-generated video actually give the patients a better understanding. However, not by a very large margin, but it is improved compared to the plain text message. On the other hand, if we try to compare the computer-generated video with a real physician recording, the patients actually prefer the real physician recording simply because it's much more realistic, because it's a recording of a real human. So that brings up a very important question. So how do we actually make the video more realistic and make the user more comfortable when watching them? So that actually goes to the second stage of the project. So the main goal is still try to help the patients to get better understanding of the medical message. However, we made some improvements. So basically, we used another software called a Crazy Talk, which is very popular to generate more realistic facial animations. And we also explored the appearance of the avatar and see which one the users actually prefer. So there are different, male, female, younger, older, also realistic versus cartoon version. So we explored many different things. We also explore the expression of the avatar. Either we deliver the message as a positive message, or we deliver it as a slightly negative message and see which one they better memorize them and motivates them. Yeah, so those are basically some of the key factors we are exploring: age, realism, and gender. So at this stage, we actually tested all of these avatars and using different medical messages. And going to the next, we are actually going to add some interactivity to the system. So basically, the system now is able to interact on a very limited base, of course, with the user and do some teachback. So just to enhance their understanding of the medical message. So those are actually interaction teachback are important concepts in the psychology. So they want to explore, which I'm not quite familiar with either, but we just implement that into the system with the virtual human toolkit. I mentioned that previously earlier. Yeah, so at this stage, so actually I'm graduating from the school, but we do have a platform with computer-generated avatar with both body and facial emotions, and with a certain degree of interaction with the patients. And they're still trying to explore more capabilities by adding some dialogue management into it to enhance the interactivity, and also do some more animation rendering to make the whole user experience much better. Yeah, that's basically rushing through of the first part of the psychology part. And for the second part, it's more of my own research. I mean, PhD thesis in the facial animation synthesis. So this part is partially derived from the first one. So basically, I noticed that the facial animation synthesis quality is very important because human beings are especially sensitive to the facial region. So a little bit of artifact will make people uncomfortable, right? That's the uncanny valley phenomenon. So how do we improve the facial animation synthesis realism? Is actually a very important and a very interesting research question. Yeah, so a little bit background or a literature review of the facial animation synthesis in the academia. So usually we classify them into two categories. So the first one, call it the appearance-based. So let me bring up the diagram. So basically, the target facial image is generated directly from a system. So in our case, it's a neural network. So basically, we have a source image, which establishes the identity of the speaker. And we have a driver. By driver, it's a different kind of driving sources. It could be audio, could be landmark, or action units, or some other people drive it with another video. But basically, a identity image and a driver. And usually it goes through a neural network in the format of a encoder, autoencoder, and it generates the target image directly. So this is what they call it appearance-based, because it generates the whole appearance at a single time. In comparison, there's another approach called warping-based. So basically, instead of generating the target image directly, the neural network actually generates a warp view. it tells us how to move those pixels around in the source image in order to generate the target image. So for example, in this one, we are moving those pixels in the lip region and jaw region in order to generate the image walking. And one question I always got asked is that how do you generate the T2's image here and in this one? Direct answer is not. This diagram showing here is only for illustration. If we only use this working system, we cannot really generate the tools inside. This I will address at the later slide. But basically, the working-based method is just generate a target vector telling us how to warp a identity image to get a target image. And as always, there's a trade-off between different methods, especially in engineering. So basically the working-based method usually have a higher resolution and better detail preservation. And they also preserve the identity better. However, they don't really deal very well with hidden regions like the tools we talked about previously. And also head movement sometimes is restricted. And also in terms of ease of integration, the working-based method usually is a little bit easier to integrate because we can apply those vectors to an image instead of the appearance-based method, which generates the image as a final output, which we can't really do too much editing after that. And the question is, which one should we choose, appearance and working-based method? It turns out that if we combine those two methods together, it can improve the final synthesized result. So this diagram here has many components, but basically the idea is as follows. We still give the network some identity images. Instead of giving them only one, as used previously, we are giving them multiple identity images. So as shown here, we are inputting 5 of them. Each of them actually has a different mouse openness in it. So from a closed mouse to open mouse, so that the tooth region can actually be included. So that information is available to the network right now. And as always, we need to have a driver, basically telling the network what is the target output should be. So this is a driver. In this work, actually, I'm using basically a difference between the input and output landmark, but that's too much detail to talk about here. So identity image and the driver, and we put it through a neural network in form of a deep autoencoder. After that, it actually branch into 2 branches. So I call them the visual branch and the geometric branch. So the visual branch is actually corresponding to the appearance-based method we talked earlier. So basically, it generates a image as the output. Instead of generating the final image, it actually generates a image representing the color change between the target and the input. So I'll talk a little bit in detail in the following slides. So yeah, so basically the visual branch generates the color difference, and the geometric branch is corresponding to the warping method we talked earlier. It tells us how to warp or moving those pixels around in the input image in order to get the output. And finally, we just combine those two together to get the final target output image. Yeah, so basically in the next few slides, I'm going to talk each component in more detail. The first one is the network input. So yeah, as mentioned earlier, we are giving the network more identity image as input to provide more information. So basically here you can see that the tooth region now is visible to the network for synthesis purpose. And the target landmark field is the driver I talked about earlier. Basically, you can think of it as an optical flow-like matrix. It tells the network what is the, so basically for the landmark in the target image, what is its relative displacement to the landmark in the input image. And it's represented as a, basically as a matrix. So that's the input. And for the geometric branch, the geometric branch is the basically the warping-based method. So the network generates a warp field. So basically, each pixel represents the direction we want to move each pixel in the input image. And the output image is actually synthesized by merging those warped image together. The question is that now there are 5 images, 5 input images, right? And after warping each of them, how do we combine them together? I mean, how do we know, which part from which image should be used? So that one is actually achieved by a source selection mask. So this one is a mask basically taking value from 0 to 1. And a white pixel corresponds to 1, meaning that that part is more selected from that image. So in this case, for example, the output is an open mouse image where the tooth should be visible. So in that case, as you can see that the source selection mask has more weight on the tooth region in the final image. And hence, it can be selected to generate the output. And here is the ground truth, basically. And so the tooth in the output is visible in this case. If we only use one image as input, then the tooth region will not be visible, simply because that information is not available to the network. Here is another example. So basically, the eye region. So this one demonstrates the eye region. So you see that the input source image has multiple ones. Some of them, actually one of them has a closed eye, others has open eye. And the target output is closed eye. So in that case, it makes sense to select this region from the first image, which you can see here from the source selection mask. It is has more weights here compared to others. So that's the as a recap, that is the geometric branch we just look at. Basically, select the relevant part from the input images and warp them and combine them to generate a partial output, which is here. And after that, it will be merged with the visual branch, for which we will talk in the next slide. Yeah, so visual branch. So visual branch, it generates a color change. And again, what do I mean by that? So basically, the first row you see here is actually still the input image with different mouse openness, as you can see. It establishes a identity. And on this row are 5 different sample output. So they are all using the same input image from the first row, but the target output is different. And the third row actually shows the output from the visual branch for each instance. So for example, for the closed eyes, actually the color change is more focused on the eyelid region. So there are more reflections on the eyelid in order to generate that reflection part on the eyelid. And if the output is more about an open mouth, then the color change actually also take care of that part by generating the shadow inside the mouth, as you see here. And the same questions arise. So basically, how do we merge the visual branch with the warp branch? And the answer is, again, a selection mask. So basically, if you look at the selection mask, In this case, black means more weight. So in this case, you see that the eyelid region is more black, meaning that more pixel values from the visual branch in this part is selected in order to transfer that reflection into the final generated output. Same as the mouse region, so more weight is selected from this shadow region to generate the final output. So in that case, the visual branch and the work branch will be merged together according to this merge mask and generate the final output. Here is a demonstration of the merging of the two branches. So basically, at the top part, you see that this is the visual output, basically the color change. And the lower part is the warped output, basically just the lower, basically warping and merging them. And using that selection mask, we actually merge those two together to generate the final output. And those highlighted region highlights the subtle parts in the final generated output. So if you see the eyelid region, the warped image only warps the pixel. However, it doesn't really generate any reflection from it. And after merging the visual branch, you see that the reflection has been added to it, which adds more realism to the eyelid if you compare it to the ground truth. Same thing happens with the mouse region. The original warped result has a actually lighter inner region in the mouse. And after merging it with the visual branch, it actually adds more shadow into it to add in the realism of the mouse region. Here are some generated quantitative evaluations, basically just different identities with different mouse shapes. So GT is a ground truth, and this synthesized basically is the synthesized output from the network. And here is another data set. So previously, this one is called a TCD-TIMIT, TCD-TIMIT data set. And the second one is the face forensics data set. So both of them are high quality video data set. And we just use each frame to train the network. And here are some animations generated by the network. Basically, we generate each frame individually and concatenate them together to get the final output. So the first row is the ground truth. As you can see, actually the eyeball of this actor is moving a little bit when he's reading. However, we are not modeling that kind of variability in the facial expression, which is why the eyeball is fixed, in the generated output. The face does move a little bit in the generated facial animation, simply because we are tracking those landmarks in the ground truth and using them in the final generated output. And another one, so this one is a face forensics data set. For this one, we have to do the facial registration because they are usually from YouTube videos and news videos, so they are not well aligned. So we have to align them by fixing the eye corner and the nose tip, which is why you are seeing this kind of a weird panning or zooming effect. Yeah, so here are some quantitative evaluation. Basically, we compare to two state-of-the-art previous methods, Ganimation and X2 phase. So Ganimation is the appearance-based only method we talked earlier, and X2 phase is the warping-only based method. And we use the L1 score as well as the FID score to evaluate them. And we can show that our method improves the score, especially at the FID, significantly compared to the previous two methods. Yeah, so here just some comparison of those methods. So one thing to notice is that if you look at the let's see which one. So basically for the X2 phase, this is the warping-based only method. If you look at the tooth region, it cannot really generate the tooth inside the mouth faithfully because that information is not available to the network. Whereas the animation is the appearance-based method, it can actually generate the tooth. However, it's kind of blurred. It lacks the detail. So by combining those two methods, we are actually able to generate both the tooth region and also in more detail compared to the either method by themselves. Yeah, again, another comparison on the more challenging face forensics dataset. The same problem is actually more prominent in the tooth region when you look closely to the tooth. So here are some ablation study, not too important to talk here. So basically, we just try different configurations of the network, by deleting some important modules, and it turns out we do see a visible degradation if we delete the modules. Yeah, so that's that is the landmark-driven part of the thesis. And after that, I simply extend that one to the audio-driven facial animation. So this one, for the audio, I'm using the MFCC as the input to generate the target landmark of the facial animation. And I use that generated target landmark as an input to my previous network to generate the final facial animation. So basically from audio to landmark, and then from the landmark to the facial image. That's a two-stage. So here is a detailed view of the network. So basically using the MFCC, and we process this MFCC also in two stages. In the first stage, we reduce the number of features, and in the second stage, we reduce the temporal length basically to get it into a single vector. And after that, we used a ILSTM actually to generate the final landmark sequence from this MFCC. So this MFCC basically corresponds to a 350 millisecond audio window. Yeah, so MFCC, delta, and so just a little bit more detail. MFCC uses delta and delta, which is the 3 here. And we use the 12 of them, and the 36 corresponds to the temporal dimension. So after reducing into a single vector, we use the LSTM to generate the so before that, we also feed the template landmark into the network. And the reason is that we don't want our target generated landmark to deviate too much from the template, which will actually change the identity of the speaker. So that's why we are feeding the template landmark into the network as well. And so we pass it through an encoder, feed it into the LSTM driven by this MFCC feature. After that, just to decode them to get the final target landmark coordinates. Yeah, so that's why we need the template input. Here's a very funny illustration, basically just saying that even after alignment, the landmark actually don't align very well with each other, which when you convert them to the image space actually will generate quite a lot of difference, which is why we provide this landmark template to the audio network. Simply just want to preserve the landmark identity. So here I will skip this one. More details on the network structure, encoder, as you can see here. LSTM, basically 3-layer LSTM, 256 number of hidden units. Yeah, as for data pre-processing, it's pretty standard. So basically, segment each audio, sample it to the same sampling rate. And for the MSCC, we use 350 millisecond audio window for each video frame. So we are using a relatively large audio window because we want to include more context into the video frame to take into consideration its neighbors. So as for comparison, we compare to another previous state-of-the-art method on the CVPR. So basically, they are also doing audio-driven facial animation synthesis. However, they are not using so they are only using, I forgot, either appearance-only based approach or working-based approach, but basically not a combined pipeline. And yeah, we are both using the MFCC as the initial input to the network. And oh yeah, so they are using the landmark PCA coefficients. So they are generating the landmark PCA coefficients, whereas in our work we are generating the landmark coordinates directly. And also we use a multiple template image, as you see in the previous section, to get more realistic facial animations. So the evaluation follows usually the standard. So we use the landmark difference MMD, which is basically a weighted out-to distance on the facial landmark coordinates. And as for the generated video quality, we use the same metric as they use in their one, which is the SSIM. And we show that we quantitatively improve both of the metrics, not by a very large margin in this case, actually only marginal. However, the visual quality does improve quite a lot because of the two-branch approach we used. So by using two-branch, we simply add much more information to the network, which of course generate a more detailed facial region. So also their network synthesizes only the central face region, whereas when we generate our network, we actually crop out a much larger region in our network. When doing the comparison, we actually only use this part to compare to them to make sure we are compared on a common ground. So yeah, so those basically are just the results from different data set. One of them is TCD TMIT, and the other one we use is the GRID data set. Yeah, so so that's a audio-driven part. And as for future works, there are still some unsolved problems. So for example, the mouse region, usually it doesn't really open enough in the audio landmark synthesis, which is called the under articulation problem. So how do we improve that? It's a very interesting research direction. Also, how do we deal with head rotation? So basically, when we talk, human head actually rotate involuntarily. So how do we incorporate that information to into the synthesis framework to make it even more realistic? So those are actually very interesting problems to explore. Yeah, so that's a talk, actually quick dart through the facial animation synthesis part of the network, of the thesis of network. Finally, there are just some other projects I did along the master and PhD project education path. So first one is called iKids. So this one is about infant gaze classification. Also, this is a collaboration between the EC and the psychology department. So basically, they want to study how human beings learn to recognize patterns at a very early stage. So they show, different images on a computer screen to the babies, and they want to know which one the babies are looking at. Problem is that using traditional eye tracking, commercially available eye tracking softwares, it doesn't really work simply because either the baby moving their face too much or the eye is not open enough for the cornea reflection tracking mechanism. So that usually fails, which is why they came to us and see whether we can find another way to do it. So I did this one during the master and early PhD stages. So basically, we use some very traditional computer vision techniques to track the landmark, which is basically a target placed on a baby's forehead. So this is a sticker. We track this one, and we estimate the head rotation by fitting ellipse onto it. And after that, we can calibrate it and crop out only the eye region for further analysis. And going from there, simply we find the iris boundary by some adaptive thresholding, and we look at the intensity to the left and right. So the idea is that the eye region has a much more intensity than the skin region, and based on that one, we can actually classify whether the baby is looking at the left or the right image. We do it on both eyes and for more robustness. Yeah, so this whole thing is basically implemented on the OpenCV on C++ on a 60 plus frame per second. And we compute the accuracy based on human annotation. So the psychology department, they actually go through each frame and label them manually. And we compare that one as a ground truth. The final accuracy is around 85%, although the variance is very high, depending on the baby behavior. It could be down to 60% sometimes if the baby have extreme head rotation angle. And in some cases, very high, up to 98% if the baby is more stationary and facing to the camera. And also, this one doesn't really require any calibration. So because the baby simply do not cooperate with the calibration process. So we just bring in the test subject and they can use it directly. Yeah, actually, a important thing to notice further is that the infrared camera, which is widely used in commercial, that one actually is going to be much better because usually they have much higher contrast. So the extraction of those landmarks as well as the eye region will be much more robust. However, at that stage, we are simply using some web camera RGB, so actually low resolution web cameras to do the experiment. Yeah, so the other work I did during the early PhD stage is the representation learning. So this one is also using a deep learning technique. So this one we called it representation generative adversarial network because the goal is actually to learn a hidden representation of the data set, which is usually an image. And the idea is briefly as follows. So there are two actually previous work. One of them is called adversarial autoencoder or AAE. The other one is called information maximization gun or info gun. So if we look at the loss function of the AAE, we can decompose them into two parts. The first one is the adversarial loss. This one is actually used to regularize the representation distribution. In our case, we are trying to push it into a Gaussian distribution. So this one, basically, this loss regularizes the representation distribution. And the second loss is the reconstruction loss. It basically says that the autoencoder need to reconstruct the image as close to the original one as possible. So that's the second term. On the other hand, if we look at the definition of the conditional entropy, we can actually derive a upper bound of the conditional of the conditional entropy, hxd. So x here represents the image, which is the MNIST in this case, and z is the hidden representation we are trying to learn, basically the bottleneck of the autoencoder. So if we compare those two terms, it turns out that the second term in the AAE is actually corresponding to the upper bound of the conditional entropy. What does it mean? So basically, it means that if we are minimizing the AAE loss, we are minimizing this whole second term. Equivalently, we are actually minimizing this conditional entropy. So here's a simple diagram to illustrate this idea. By minimizing this entropy, I'm saying that given the hidden vector, which is, for example, slime 24, I'm minimizing the entropy of the image given this hidden vector. So that usually means when it comes to image generation, a sharper image. So basically the image will have a sharper edge and represents better this hidden representation. So on the other hand, the infoGAN is the other way around. So basically, if we look at the second term of the infoGAN loss compared to the conditional entropy of the hidden vector z, given the image in this time, so it's reversed, right? So we can see that they're actually the same. So using the same argument by minimizing the hidden vector, the hidden representation given the image, we are actually getting a better classification result. So basically, given all those kind of 6, in different styles, we can all correspond to them to a digit 6 instead of confusing them with digit 4, digit 5 kind of. So basically, minimizing the uncertainty of the predicted label given those images. So using those two into this one is visible. Let's skip this one. So using this intuition, we are arguing that if we train the network in 2 directions, so basically in the AE fashion and also in the infoGAN fashion, we can actually get a better bijection mapping between the image and the hidden representation. So basically, in this case, we are squeezing them, in both directions so that they can correspond to each other much better. So, which means a better reconstruction quality as well as a better classification accuracy when using either one of them standalone. So that's the intuition behind this work. And we carry out the experiment. We train them actually using this this idea in 2 directions. And here's the result. So we try them on multiple data sets. So for MNIST, which is very popular, we show that actually our classification accuracy is higher than either of them standalone. And the reconstruction error is lower than the infoGAN, however, still higher than the AAE. So this one is sitting in the middle ground for the MNIST dataset. As for the fashion MNIST dataset, which is a different kind of close, it still has a better accuracy, and in this case, we are actually getting a better reconstruction error as well in terms of reconstructing those close images. So here are just some comparisons. So AE infoGAN and our representation GAN. We also try the generation capability. So basically, by varying the hidden vector, we are actually getting different images in different styles. So in this example, as we can see that we vary the rotation of the digits as well as the stroke of the digits along 2 dimensions. In this case, we are just varying the style of each shoes, like from a boot to a lower ankle boot, or different styles of the shirt or the high heel boots as well. Same thing with the SVHN, the street house number dataset. We are varying the color along this direction as well as the number along this direction. And finally, we tried it on the celeb-A facial image dataset, and we showed that we can actually vary the facial hair attribute. So this one is actually much more coerced compared to other datasets, but still it shows a trend on the facial hair along this dimension, as well as the openness of the mouth along this dimension. Yeah, okay, I think that's pretty much I'm gonna talk for today. And here's a final, basically, thank you slide. I call it system diagram because it's really a collaboration between different parts. So, so my advisor, Thomas Wang, as well as Mark Johnson, so we're from the EC department. We are collaborating with Professor Daniel Morrow from the psychology department for the avatar projects, and some other students from both the departments to make this whole project work. Yeah, with that, I would like to say thank you very much.
Kevin, thank you for the presentation. So any questions, comments for Kevin? I will start off here. I have a question for you, Kevin. So to me, it seems like these conversational agents are just one way. How do the physicians or healthcare providers feel about that, where we have these conversational agents communicating to the patient, but then the physician is not there to understand the nonverbal communication coming from the patient back?
Yeah, that's indeed a very good question, because it does include quite a lot of liability problems, right?
Okay.
Yeah, so we haven't really tested on a real world scenario which requires much stricter clearance. So the idea is not really to replace the physician. So we cannot replace them. It is more like an augmentation. So usually, like for example, the physician will write some inscriptions to the patients, or write some instructions for them. However, it may not be immediately understandable by the patients. And we put it through the system, do some translation as well as medical term simplification, and we add in an avatar with the matched emotion to it. So we use this one actually as a augmentation and as a how to say, some kind of offline help to the physicians, so that the patients can better understand the message. So we are not really generating anything new. We are actually augmenting them.
Okay.
That's the general idea.
Okay. I get it. Yeah. So complementary to what the physician is doing. So I can see a lot of benefits, like in situations where there's like one doctor for a small town, and it's hard to reach the patients, by the doctor or the physician having to travel to the patient. So using technology is a good way to perhaps get to the patient without being there physically.
Yes, saving the physician's time is also a very important thing. I think I forgot to mention. So basically, many patients, they get re-hospitalized, or they just come back for a very simple check, or sometimes to ask a simple question, do take a lot of the physician's time. They are already very busy. So we are also hoping to address that situation, use this kind of platform.
Yeah. Questions, comments?
Yeah, so this one I probably darted through a little bit too fast, sometimes not much detail, but usually I don't talk this much in maybe a month or so. So feel free to ask question here, or either afterwards if you have anything pop on top of mind.
Sure.
I got a quick question, if I could.
Yeah, sure, Justin.
Yeah, sure. Cool. Wasn't sure if my microphone was on. Yeah, so I guess I'm wondering, with all the deep fake stuff going on, I guess, where people
Yeah.
can do negative things, I guess. You know, I see some of the positive things, but how do you see this possibly being used in a harmful way?
Yeah, well, usually the technology itself is neither evil nor good. It's the people, how to use them.
Right.
So yeah, deepfake, that kind of thing does pose a very serious problem. Actually, I know that in some country, the bank system, they try to use facial animation for verification. However, they already got people trying to use this kind of technology to crack that security system. So that is a very real threat. Yeah, I don't know how to answer that because I don't really control it. But maybe maybe we can add some hidden information into the bank images. So you know that there are topics as called adversarial attack, right? So people use the adversarial network to generate some images that is perfectly fine to human eyes. However, it's going to be problematic for detection systems. So maybe reverse. So using that technology in a reverse way, we can add some very subtle detail into the bank images, and it passes through, to the output, so that people cannot use that one to do some illegal things like that. But again, this is a very cool thought. Somehow we have to enforce this kind of information to go through the network to make it work. Otherwise, it doesn't really make too much sense.
So could you actually then, I guess, use the analysis to then prove that it was actually incorrect, that it was a fake? I guess I'm just trying to think if there's some sort of a algorithm you could come up with to realize when things were not correct using this methodology that you have.
Yeah, actually, that one you mentioned, there are already research on this one. So basically, they are using deep networks to distinguish whether a generated video is real or fake.
Yeah.
The idea is actually like follows. So you remember the mask I'm talking about, right?
Mm-hmm.
So if you look at their research, their network actually only focus on usually some very specific region on the generated image. I know that they focus on the eye corner, they focus on the mouse corner. So basically those small regions. And their network shows that they put much more emphasis on those small regions when it tries to distinguish between the real and the generated videos. Yeah.
Interesting.
Yeah, because those details are actually very hard to generate. So because I mean, as a human, when we look at a big image, at the very first glance, we see that okay, this is realistic or something. However, when you zoom in, you may find some small artifacts that's not really addressed. So I think they use this concept to train a network to distinguish it.
Sure. Yeah, there might be some sort of a signature, in there that's kind of just a trace artifact that then you pick it up. Interesting. Yeah, that's really cool.
Yeah, actually, I'm just thinking maybe something like for the skin color, because when humans look at an image, we actually internally average them, right? So we internally average this part so that it's a uniform skin color. Maybe we can embed some kind of cross pattern into it, which will not be sensitive to the human eye, however, can be very easily picked up by the algorithm, I guess. Something like that, yeah.
Made me think about counterfeit bills, counterfeit dollars,
Yeah, so I think they use that kind of stuff, yes. Yeah, actually, very good question. So just elaborate a little bit more. So basically, for most of the neural network, research you see nowadays, people don't really put too much engineering into the network, right? I mean, on one thing, that is the idea. Just let the machine do the work, let the data do the work. On the other hand, we don't really know, again, what is happening inside. So take the facial animation synthesis as example. We don't really know what the network learned. Maybe it learned a muscle model underneath, or maybe it not. Maybe it learned something totally different. We don't really know that. So that is kind of so that actually make it hard to generate a completely real image, right? So sometimes, there will be some artifacts in very subtle details, but we can't really control that because we are not really looking into details here.
Nice.
Mm-hmm.
Hey, Kevin, there is a question in the chat from Adam, and Adam is asking, how did you get to this point in your career? Like what prompted you to choose this line of research? He's just starting out, yeah. So Adam is starting out in his career, so he's curious how you got started in this space.
Let me read. How did you get to this point in your career? Surprised face. I'm just starting out. What could possibly go wrong? Just think of the potential. Yeah. So I'm actually working. So yeah, that's a good question, because when I first started in the undergraduate and master school, I was more focusing on the signal processing stuff. So basically, Fourier transformation, other imaging kind of stuff. Later on, when I get into this avatar project, which is the first one I talk about, I realized that there's a problem in the facial animation synthesis, research. So basically, how to generate them more realistically. And also, I'm in the verge of neural networks. So, in the last few years, the neural network has been developing quite a lot. So that's actually what motivates me to go through this path. Basically, combining the what we did before about facial animation synthesis, put it into a deep learning framework and just try it out, and it turns out to be working. So yeah, short question is that I didn't really plan that much far ahead. I would say probably the just the direction of the research and the technology guided me through this one. Nonetheless, it's actually a very interesting problem to study. What could possibly go wrong? I'm not quite sure what does that mean. I mean, you could blow up your GPU when you're training it. That's bad enough. Just think of the potentials. Yeah, if you are trying to ask about the technologies being used by bad guys, that is always possible and actually almost guaranteed. But I mean, as research, I'm only interested in how we make things work, I guess. That was a joke.
Kevin, so you mentioned earlier your talk, like this kind of technique is not used currently in the film industry yet because of the quality. So do you see any like possibility that this kind of thing can be used in near future in the actual film industry or entertainment industry?
Yeah, I'm not seeing this kind of a neural network-based facial animation generation in the industry. I probably didn't say exactly that one. I think I didn't see the texture-based system used. Neural network-based facial animation synthesis, I'm not quite sure whether they are using it right now. However, if you ask me to just give it a guess, I will say it probably won't be very popular in the industry, simply because if you think about it, the network, you train it on one data set, and you are trying to generate something like a King Kong or Avatar. I can guarantee it doesn't work, simply because the modality of the data set is so different, and you cannot generate such a high fidelity, film level, animation from it. On the other hand, those traditional systems are actually very well developed. So you see those facial tracking kind of thing. They are modularized very well so that they can integrate it with each other with much more flexibility. That being said, it's hard to predict because that some of the deep learning technique has already been deployed in the industry and consumer, like DLSS, right? Deep learning super sampling. So that is actually a very good example of deploying into the real world. So that one works. So maybe we are just, not on that stage yet. Maybe in the future, if we got some more complicated model or some different paradigm, we might be able to actually model the physical process under the hood and actually make it realistic enough to deliver it to the film industry. But probably not happening in the future. I mean, in the near future, I guess.
Okay, yeah, thanks. Yeah, I was just wondering if this film company is actually putting their effort on developing or this kind of technique, or if they have some research department doing this.
Yeah, that's a good question. So don't quote me on this one. But also, I think it depends. It depends on on which level we are trying to tap in, right? So are we trying to tap in from an end-to-end approach? So basically, for example, the actor says something and the network directly generate a fully rendered, image from that. Let's say end-to-end, probably not. But how about some intermediate approach? For example, the actor says something and the network generates the facial landmark locations as an intermediate step. After that, we put that into whatever powerful rendering software we have to generate the final output. So basically, we're bypassing this, this kind of funky setup. So that might be more realistic approach instead of doing a full end-to-end approach, I guess.
Thanks. Yeah.
Yeah, but yeah, you never know. Industry, maybe they throw 500 GPU into it, and so all of a sudden it works.
Yeah, right.
All right. So we're close to the hour here. So any more comments? All right. So Kevin, on behalf of the AppliedAI Meetup, I want to say thank you so much for presenting this evening. Thank you for educating us here. And it's always interesting to see how technology is moving forward, and how when it comes to a time when I think that technology is gonna replace humans, then I see from like a presentation tonight where the experienced professionals, the humans, being complemented by technology and vice versa to deliver meaningful outcomes for people. So this is great to see.
Yeah, thank you very much, Eric. Not really educating you guys. I mean, not at all. It's really more of a discussion because as one people, usually we think of something probably not from a very broad perspective. Discussing it with other people usually helps with the process much better. As for technology replacing human, I wouldn't worry too much for my left, I guess. I mean, we have been evolving for so long. The idea is that technology, so they are very fast and sometimes very good at a specific area, right? However, it does really lack the domain knowledge. So, for example, those kind of facial animation synthesis, it only synthesizes the facial animation based on the data you gave it. However, it does absolutely not know how those muscles move under our face, or how those pronunciation drive those muscles. So it doesn't have those kind of knowledge. Those knowledge are possessed by human beings, or sometimes we call experts. So I guess it make more sense to me that we can use such kind of technology as a augmentation to our process to reduce human being error, or to accelerate either development or production. But to completely replace that probably has some way to go, I think.